Once again, thanks for joining. In today's webinar, we will be discussing about this lightning protection system designing for mainly oil industry. So if you take the number of lightning strikes is keep on increasing and the damages due to lightning is also keep on increasing. But why this lightning protection system is separate for normal buildings and oil storage areas, and why additional protection is required? Because in oil storage areas, we are having highly flammable materials which leads to explosion due to this lightning. So that is the reason if you are taking this oil storage areas, they are highly high risk zones, particularly to this lightning protection system. So in today's session, we will be mainly concentrating on how this lightning protection system is different for oil and gas industries, and what is the standard specifications regarding the designing of lightning protection system, and how can we place the lightning air terminals, what are all the different materials that can be used, what should be the height of the air terminals, and whether the lightning air terminal can be mounted on the structure itself or we have to isolate them from the structure. So these are the topics we will be covering today. So before entering into the topic, let us provide a small introduction about CIKIT. CIKIT was incorporated in 2018. Even though it is a 6 years old company, we are having an experience of more than 17 years in this field of lightning protection and earthing. Our specialization is we are providing complete end-to-end solution for both lightning protection as well as the earthing. So end-to-end solution in the sense we are providing performing site analysis, performing risk assessment calculations, designing of lightning protection systems, material supply, installation, and if you are having already existing systems, we will perform the auditing for ensuring the healthiness of the system. So we are providing end-to-end solution for both lightning protection as well as this earthing. And our one more specialization is we are providing customized solution rather than going for a generalized solution, which means if you take this oil and natural gas industries, the standard which we follow for oil and natural gas industries will be separate. So the Oil Industry Safety Directorate has provided a set of instructions that has to be followed while working on oil and natural gas industries. But when we are working for buildings, then we'll be referring to 62305 and National Building Code NBC 2016. So when we are working to any specific site conditions, then we will be referring to the standard that is very specific to that particular industry rather than going for a generalized solution. So there is uh, another specialty of us. Right. So as I mentioned, these are the different standards which we follow for this lightning protection systems. So if you observe for the oil industry, we will be referring to OISD GDN 180, which is the standard published by Oil Industry Safety Directorate, which will be coming under Ministry of Oil and Natural Gas Resources. And then we'll be referring to NFPA 780, then API that is American Petroleum Industries 545. These are the different standards and codes that are related to designing this lightning protection system specific to this oil industries. Right. So everyone will be aware of this particular train accident. So in 2023, the train accident happened near Odisha, and almost 289 people lost their life due to this particular train accident. And for more than 7 to 10 days, almost all the national and international media covered this particular train accident, and they did proper analysis for providing what is the reason for this particular train accident and how can we avoid those accidents in the future. So like that, many people started working on this particular train accident, and it happened for more than 7 to 10 days. But if you take this number of deaths due to lightning, which is almost 10 times higher than the death caused by that particular train accident in a year. So in a year, almost more than 2,800 people are losing their life only because of this lightning. But no one is providing proper importance to this lightning protection system because the deaths are happening from the January to December, and almost it is not happening on the same time. So in January, in some places the death will be happening. In December, the death will be happening at some other place. So since the count number of deaths is high, but since it is happening at different times at different locations, we are not giving proper importance to this lightning protection system. So if you take the quantity, that is the number of deaths, it is almost 10 times higher than the number of deaths caused by this particular train accident. So if any lightning is striking on a building or normal structure, then it may result in failure of the particular structure. Like it may result in damage to the structure alone. But if the same lightning strikes on any oil tanks, then it will result in huge explosion because this contains highly inflammable materials. If the temperature increases suddenly and if there is a small spark happens, then the small spark will trigger a huge explosion. So that is the reason we always classify this oil and natural gas storage areas as a high risk zone, and while designing this lighting protection itself, we'll be considering the level 1 protection or level 2 protection. So these regions are highly inflammable materials and the risk of fire and explosion is very much higher on this particular oil storage areas. So they need additional protection than this normal protection which we are giving. So before entering into this protection measures, let us have an outlook of what is actual lightning and how this is causing the damages. So if you take this lightning, there are mainly there are three types of lightning. So many people will be having a common idea that the discharge happening from cloud to ground alone is the lightning, but that is not the case. There are commonly three types of lightning are there. One is if the discharge is happening within the same cloud, it is called as intra-cloud lightning. So if the discharge is happening from one cloud to another cloud, it will be called as inter-cloud lightning or cloud to cloud lightning. So the third type is cloud to ground lightning. So this is the normal type which we will be considering for protections and all, because here the discharge is happening from the cloud to the ground. So this is the only type which causes the damage to the structures. It causes explosion. It causes loss of human life and all. So that is the reason for protection purpose we'll be considering this type alone. But additionally, there are two types are also there. But in addition to this, there is one more very rare phenomenon will be happening where the discharge will be taking place from the grounded objects to the cloud. Usually, it will be seen in a volcanic mountain top or a highly charged structures and all, where it will be a reverse. The discharge takes from the ground to the cloud. What actually happens during this lightning condition? So many people will be having a common idea that during the lightning, discharge is taking place from the cloud to ground alone, but that is not the actual case. During the lightning condition, that is when the lightning is forming at that particular time, it will induce the opposite charges on all the objects that are connected to the ground. For example, if the discharge is taking place from the negative portion of the cloud, that is bottom portion of the cloud, then as we know, the air is a dielectric. So if the charge builds up too much on the cloud, it will result in breakdown of the air molecules behind the cloud and the negative charges will start to discharge. So if these negative charges are discharging from the cloud, these negative charges will induce positive charges on all the objects that are connected to the ground. So here we have considered only the tree and the ground. But in case if any person is standing here, then in that particular case, the person's body also will be sending this positive charge. So if there are any person standing, then the person body will be sending positive charge. If there is a building or structure, then the particular building or structure also will be sending this positive charge. So the point which we have to note down is it is not like that only the tallest structure or the tree alone will be sending the positive charge. All the objects will be sending the positive charge, but the path will be closed through the positive charge which reaches this negative charge first. In this particular image, if you observe, the tree is also sending the positive charge, the ground is also sending the positive charge, but the tree is sending the positive charge from a different altitude. So the positive charge from the tree can reach this negative charge first. So that is the reason the path will be closed through the tree. So if there are any buildings or structures available and which is taller than this building, sorry, this tree, then the positive charge from the tree may reach this cloud from, so the path might be closed through the building. So it is not like that only the tallest structure will be sending the positive charge. All the objects that are grounded will be sending this positive charge. So this one was actually captured using a high-speed camera. So here you can observe that the lightning discharge is happening from the cloud. At the same time, the building is also sending the opposite charges. So here you can see. So from the top, this one is one streamer. Here, this building is sending one streamer. There is one more streamer here. There is one more streamer here. So from this we can observe that it is not only the taller structure is sending this streamers, all the objects will be sending this positive charges, and the path will be closed through the positive charge which reaches this negative charge first. Here you can see this one will be reaching this first, so the path might get closed through this particular streamer. So actually this is a video, but I'm unable to play the video. You can get this video on this particular link shown below. So this is citekdaily.com. So here they have actually published the video. It is a very nice video to watch. So I will play the video at the end of the session. So they have captured this using a high-speed camera at 40,000 fps. So at 40,000 fps only they were able to show the different stages of lightning formation. Impacts of lightning strike. So many people will be having a common idea that if lightning is striking directly on a structure, then only it will result in damages. But it is not the actual case. So if lightning is directly striking on a structure and causing the damage, it is considered as direct effect of lightning strike. But apart from this direct effect, lightning will cause damages through the indirect effects as well. So indirect effects, which means the lightning will be striking at some other point and the damage will be felt at some other point. So the most common example for the indirect effect is when I was a child during this rainy condition, I was not supposed to watch the TV. My parents will turn off the TV and they will even unplug the TV from the power supply. So the reason they mentioned was if lighting is happening, you should not watch the TV, it will damage the TV. So at the time, whether knowingly or unknowingly, for protecting this electronic equipments, we used to unplug the TV from the supply. Here, what actually is happening is similar to lightning striking on any building or structure, lightning can also strike on the power line. So if lightning is striking on any power line, the surges will be traveling through the power line, and for our house, we are taking power supply from this power line only. So the surges will enter through the power line and it will result in failure of electronic equipments. So that is the reason, without knowing the actual reasons, we unplug the TV for protecting this electronic equipments from the surges that might be traveling. So in this case, that lightning is striking on the power line. So the point of striking is different, and we are facing the electronic equipment failure inside the house. The point at which we are facing the damage is different. So this will be considered indirect effects of lightning strikes. So the standard has generally provided four different sources through which the lightning will cause damage. The first source is known to everyone, that is lightning striking on a structure. If lightning is striking on a structure, then obviously it will result in damage to the structures, failure of electronic equipments, and injury to the human beings. And the second source is lightning striking near the structure. So if lightning is striking near the structure, then because of the ground potential rise, uh, failure might be happening due to the surges. And third source is, as I explained, lightning striking on the power line. And the fourth source is, we found this is the most underrated source. That is, many people are not giving proper importance to this source, and we have investigated many industries. And in many industries, the reason for the electronic equipments was found to be lightning striking near the power line. Even though if we have installed this lightning protection system, if we clamp this down conductor of lightning protection system near a power line or data line, then the surges will get induced. So we know that whenever current flows through any conductor, magnetic field will be produced. So even though it is a PVC insulated cable, the insulation will be only for the electrical, but not for the magnetic field. So if I'm taking through an insulated cable also, the magnetic field will be produced, and if this magnetic field couples with this power line or data line, the surges will get induced. So that is the reason, even though if you install this external lightning protection system, the electronic equipment inside the house may fail. So, for example, if I'm having a down conductor and if a current is flowing through this means, then magnetic field will be produced surrounding this conductor. So the magnetic field will be in the form of concentric circles, and if I have any power line or data line near this, this magnetic field is linking with this particular conductor, and I am connecting this particular conductor to a equipment. So because of the surges induced on this power line or data line, the electronic equipment may fail. So here there is no direct physical connection between these two conductors, but because of this magnetic field coupling, the surges get induced and it resulted in failure of electronic equipments. So in many industries, the failure of electronic equipments are found happened because of the lightning strike near the power line. So if we want to provide a complete protection, then we need to ensure that we are covering all the four sources through which the lightning will cause the damage. So if we cover all the four sources, then we can ensure that the complete protections are provided against this lightning. So if you take this providing solution for this lightning, there are different processes involved, and the first process is performing site analysis. So if the site analysis is done properly, then almost 50% of the work is done at that point itself. So during the site analysis, we have to check what are all the possible ways through which the lightning will cause the damage, and we have to provide a solution for arresting all the ways through which the lightning will cause the damages. So the second step is performing risk assessment calculations. So we cannot tell that all the buildings require lightning protection system. That is, lightning protection system is not mandatory for all the structures. So before performing the design, first thing is we need to decide whether lightning protection is required for this particular site or not. So if lightning protection is required, then only we have to proceed to the designing. If the lightning protection system itself is not required, then there is no need for going for the design. So the that will be decision will be made on this particular risk assessment only. And based on the output of risk assessment, we'll be performing the design, then material supply, then installation. Then the most important thing is periodical inspection. So all these components are installed outside, so they are more prone to corrosion. So periodical inspection and maintenance are very much essential to ensure the healthiness of the system. So 62305 is the general standard which explains about the designing of lightning protection system. In the 62304, there are four different parts. The first part is um, explains about the general terminologies like what will be the waveform of a lightning, what are the different levels of protection, what will be the differences between the different levels of protection. So it explains about the different parameters that are related to this lightning. And the part two explains about this risk assessment calculations. As I mentioned, this risk assessment calculation will explain whether lightning protection system is required for the particular site or not. And if lightning protection is required, then what is the level that is we have to provide? So if you take this lightning protection system, there are four different levels out there. And the difference between these four levels are nothing but the efficiency. So if you take this level one protection, then the efficiency will be 99 percentage. So if you take this level 2, the efficiency will be 97 percentage. So if you take this level 3, then the efficiency will be around 91 percentage. If you take this level 4, then the efficiency will be around 84 percentage. So if we are working for a normal residential building, then if we are going for level 3 or level 4, that will be more than sufficient. But when we are working with oil and natural gas industries, or when we are working with hospitals or highly explosive areas where the risk of fire and explosion is high, then for those cases we have to go for level 1 and level 2 protection, because even a small uh, spark or accident will result in a huge explosion. So usually for this oil and natural gas industry, we'll be considering either level 2 or level 1. Then based upon the risk level, we'll be designing what will be the suitable level of protection. So if you take this risk assessment calculation, there are mainly two outputs. One output is whether lightning protection is required or not, and the second output is what should be the suitable level of protection for this particular site condition. So if you note down, in this risk assessment itself, we are calculating the level of protection. So based upon the level of protection we'll be performing the designing. So that is the reason we always consider the risk assessment as the first step of designing. So if you observe, all the design methodologies depends upon the level of protection. So that will be decided from the risk assessment calculations only. And in 6 to 3 part 3, they have explained about this external lightning protection system. And if you refer to the 6 to 3 part 4, they have explained about this internal lighting protection system, like providing surge protection devices for protecting the electronic equipments inside the building infrastructure. So that part is explained in 6 to 3 of 4. So if you take this external lighting protection system, there are three main components of the one is air terminal, second one is down conductor, and third one is earthing. So the air terminal is the component which intercepts the lightning. That is, it is the component which makes contact with this lightning source. So it should have sufficient capacity to withstand the lightning impulse current. At the same time, it should be able to withstand this huge mechanical stress due to the heavy wind and all. So this air terminal should have sufficient mechanical strength as well as this electrical strength. Then the down conductors are nothing but it will be acting as a bridge between this air terminal and the earthing. It will be simply passing this energy from the air terminal to the ground. And earthing, it will be dissipating the energy into the ground without increasing the ground potential. And these are the three main components of lighting protection system. Apart from this, there are two optional items are also there. One is testing, which is used for the maintenance purpose, and the second one is counter. So the lightning counter is a registering device which will be used for registering the number of lightning impulse current that will be flowing to the particular conductor. So it does not do anything else. This readings are used for performing this root cause analysis for analyzing the failure reasons. So the standard has explained about three different methodologies through which they can place the gas terminals. So if you take the 62305, that is the basic standard. From that particular standard only, all the standards have taken the control. So if you take OISD GDN 180, they have also referred to the same standard, but they have explained this methodologies along with the application. So how can we apply this particular method for oil and natural gas industry? So the basic standard is 62305. From this only they have incorporated these three protection methodologies, and based upon that they have explained with this application. So how can we apply these methods for an oil and gas industry? So the three methodologies are protection angle method, mesh method, and rolling sphere method. And we can use these conductors in the form of rods or catenary wires or mesh conductors. So the first method is protection angle method. I'm just providing an outline about this method. We have already conducted a separate webinar for this designing of lighting protection system. If you want more details, then you can refer to the particular video in our YouTube channel. We'll be sharing this particular video link in our chat box. So in protection angle method, from the name itself, we can understand that the protection depends upon the angle. So if you observe this, the angle on the corner air terminals will be different on different sides. So on the right side and left side, the angle will be different. This side, the angle will be different, and on this another side, the angle will be different. So the angle is different because of the height. On the right hand side, the reference plane is from the ground, whereas on the left hand side, the reference plane is from the terrace level. Since the height is different, the angle will be different. If the angle changes, then the radius of protection also changes. So in protection angle method, the protection depends upon the angle, whereas the angle depends upon height and the level of protection. So this is the graph provided by the standard for obtaining this angle for different heights. For example, if I take 10 meters of height, then I have to extend a line from 10 meters, and I have to check if I'm going for level 1 protection, I have to take this angle, that is the point where it is intersecting this level 1. If I'm going for level 4, I have to take the angle, that is the 10-meter line intersecting the level 4. So from this, we have to obtain the angle. Then by using this tan theta formula, we have to calculate the radius of protection. So we have already performed the calculations and we have found out this angle for different heights. So here you can observe that for 10-meter height, as shown in the example, the angle will be 45 degrees for level 1. In level 2, it will be 53 degrees, and for level 3, it will be 61, and level 4, it will be 64 to 65 degrees. For corresponding angles, we have find out the radius. So if you take 10-meter height above the plane, the radius will be around 21 meters. So this is how we have to calculate the radius of protection for the protection angle method. So this method we have been using for a longer period, and one practical example for this kind of protection angle method is um, the overhead transmission lines. In the overhead transmission lines, you can observe that there is a ground wire or shield wire at the top of the tower. So the purpose of this ground wire or shield wire is to protect this conductor from direct lightning strikes. So there is one example for protection angle method. The second method is mesh method. In this mesh method, we will be laying the conductors in the form of mesh over the structure to be protected. Again, here the spacing between the conductors depends upon the levels of protection. For level 1, we will be going for 5 by 5. For level 4, we will be going for 20 by 20. But we normally won't use this method for this oil tanks. But we can use this method for any other structures like control rooms, security rooms, and other administrative blocks in this oil refinery plants. And the third method and the most commonly used method for designing this lighting protection system is the rolling sphere method. Here, we will be rolling an imaginary sphere over the structure to be protected. And in this method also, the radius of protection, the radius of the sphere depends upon the levels of protection. For level 1, the radius of the sphere will be 20 meters, whereas for level 4, the radius of sphere will be 16 meters. So if you observe, in all the three methodologies, the level of protection plays an important role. So that is the reason we always consider risk assessment as the first step of performing the design. And we have conducted a separate webinar for the risk assessment also, and we'll be sharing this link for the risk assessment in the chat box. So you can refer to the particular video for more details about this risk assessment calculation. What are all the various factors involved in calculating the risk assessment that we have explained in a separate 1 hour webinar session. Here for in all the cases, we cannot roll the sphere over the structure and we cannot check whether the sphere is making contact or not. So that is the reason the standard has provided the formula for calculating the distance between the two air terminals so that the sphere won't make any contact with the structure to be protected. So we can use this particular formula for calculating the maximum distance between the two air terminals. The point which we have to note down is in this particular methodology, we are calculating the maximum distance between the two air terminals, whereas in protection angle method, we are calculating the radius of protection. So these two are not same, these two are different. And if you observe this formula, you can observe that it depends upon two parameters. One is penetration distance and second one is radius of protection. So the radius of protection depends upon the level of protection, whereas the penetration distance is the distance up to which the sphere is coming below the center. So if I increase this distance between two atomers, more portion of sphere will be coming below. And if I increase further, then the more portion will be coming below. And if I increase more, then the sphere will be making contact with the structure to be protected. If the sphere is making contact with the structure, then the particular portion will become unprotected. So if the sphere is making contact with the structure, then which means that the penetration distance is equal to height of the atomers. If the penetration distance and the height are equal, then the sphere will be making the contact. So, if we want the sphere not making contact with this particular structure, then we should ensure that the penetration distance is always lesser than the height of the air terminal. So, we have performed the calculation and we have shown this distances for different heights and for different levels. So this is the reference provided by the standard OISD GDN 180. So we will be using these three methodologies, specifically those two methodologies for this storage tanks. So OISD GDN 180 states that if the tank wall thickness is more than 4.8 mm, then there is no need for providing additional air termination system and down conductors. We can directly connect the body of the tanks to the ground. That itself is more than sufficient because if any lightning strikes on the particular tank itself, the temperature increase won't be that much and it won't result in explosion at all. So the body itself can act as a natural component of lightning protection system. So if the wall thickness is lesser than 4.8 mm or if you don't want to take any risk and if you want to ensure 99% of protection, then we can go for any of the three protection methods stated by this particular standard. The three methodologies explained by this standard are use of lighting air terminals, use of mask around the tank, and use of overhead shield wire. So these are the three methods explained by this particular standard for providing the protection for this particular tanks. So the first methodology is placing air terminals on the tank itself. So here they have mentioned that we can directly place this air terminal on the tank wall itself. So OISD GDN 180 has highlighted that 6-meter high conventional air terminals can be used around the perimeter of the tank, and one more thing is we have to place at a distance of around 20 meters. So at every 20 meters we have to place one air terminal, and if we are placing at every 20 meters, this means the distance between the atom is 20 meter, and since this is a circle, then the perimeter will be pi into d. Pi 2 pi r is the perimeter of this particular tank. So if I am placing it every 20 meters, then the number of air terminals required will be pi d by 20 or 2 pi r by 20. That is the formula which we can be used for calculating the number of air terminals. So the point which we have to note down is the height of the air terminal has to be 6 meter above the tank, and we have to place at every 20 meter spacing. So here if you observe, the diameter of the tank is 50 meters and we are placing air terminals at every 20 meters. So if we are going for this particular methodology, then the radius will be it will be around 15 to 18 meters will be the radius of production. If it is 50 meters, then there will be some portion in the center that will become still uncovered. So if we are going for 50 meters and if I am placing the air terminals along the perimeter, then the center portion of the tank is still unprotected. So that is one of the drawbacks of this particular methodology. Here, if you observe, the diameter is 50 meter and the number of air terminals are 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 air terminals placed on the along the perimeter of this particular tank. So they have already performed this calculation. They have provided uh, the number of air terminals required for different tank dias. So if you take this particular category, this one will be coming under 46 to 51 meters. So if you observe here, for 46 to 51 meters, we require 8 number of air terminals. So we have checked here also. So here also we have placed around 8 air terminals. But the drawback of this particular method is the center portion is become unprotected. This area is not protected by using this particular method. The second method is by using lightning mask. So here we won't be placing this air terminals on the structure itself. The reason is if it is an existing plant and if I want to install it, the welding of air terminals is not allowed inside those particular areas. So if that welding will result in fire accidents and all. So if you don't want to weld any other structures or if you don't want to make any alterations in the tank body, then we can go for providing this mask surrounding this perimeter. So here, in order to avoid this dangerous flashovers, we have to maintain a spacing of around 6 meters between the tank body and this particular lightning mast. So if you observe here, they have maintained this 6 meter spacing. That is that between the tank wall and the lightning mast, we are maintaining 6 meter spacing. So in order to provide the same protection similar to the 6 meter height air terminals on the wall, we have to provide 12 meters, sorry, 15 meters height. So the height of the mast has to be 15 meters above the tank wall. And here also at every 24 meters we have to provide one particular air terminal. So if we keep like this, then we can the protection provided by this method will be almost similar to the protection provided by the previous method. And in this method also, if you observe, the center portion is still unprotected. So this is a drawback of these two methodologies. And the standard has highlighted that the lightning protection mask, the earthing of lightning protection mask can be bonded with this tank body earthing. So the earthing can be bonded. Then the third method is by using overhead shield wire. So the drawback of this first two methods was the center portion of the tank was still unprotected. So if you want to protect the entire tank area, then we have to go for this overhead shield wires. So the shield wires will be laid between the tank poles. So here there will be some conductors on the center portion also. So here you can see. So since we are having these two poles along the internal, by using this rolling spear method, we can observe this. The tank is protected along the entire area. So the even the center portion of the tank is also protected by this. And we need to ensure that the clearance is around 8 meters. So from the top of the tank to the catenary wires and the rolling spear, we have to maintain a clearance of around 8 meters. And here also we have to maintain the spacing to avoid this flashovers between the tank and this lightning mass. So by using this particular type of arrangement, we can ensure that all the portion of the tanks are protected. So the standard has also provided how many masts are required for protecting this tank for various diameters. So if the tank dia is between 8 meter to 30 meters, then we need only two things. So here it is 30 meters. So for this 30 meters we require only two wires. But if the tank dia is between 30 meters to 8 meters 80 meters, then we require only three. So we may require one more wire at the center portion. So this arrangement is more than sufficient for protecting the tanks of diameter up to 80 meters in diameter. So these are the three different methodologies suggested by the standard for protecting these tanks from direct lightning strikes. So the standard has highlighted that we can use different materials for lighting protection system. So we can use copper, we can use hot dip galvanized steel, we can use stainless steel, we can use aluminum for this lighting protection system. And the most important point to be noted down is the galvanic corrosion. So we know that normal corrosion will be happening when we expose iron material to the normal environmental, but this galvanic corrosion is due to the chemical reaction between two dissimilar materials. So if I connect aluminum and copper together, because of this difference in chemical properties, the aluminum will corrode much faster than the other material. Then that is this type of corrosion is called as galvanic corrosion. So aluminum and copper should not be directly connected. It will lead to galvanic corrosion. So whenever we are working with multiple materials, then we need to ensure that we are not connecting these materials which are having different potentials. This is the recommendation provided by 62305 for selecting the material dimensions. So here you can observe that we can use copper, aluminum, or dip galvanized stainless steel, copper coated steel, and for each and every material they have provided different configurations also. So it is not like that we have to go for only rod. We can go for strips, or we can go for even standard conductors like cable also. For each material and for each configuration, they have provided what should be the minimum cross-sectional area. So these values are minimum cross-section areas. And if you observe it clearly, for the copper itself, for solid tape is nothing but strip configuration. Solid round is nothing but rod configuration. The standard is nothing but similar to the cable. And the fourth one is also round. Here the difference is first three are for down conductors, whereas the fourth one is for air terminal. So we know that if a lightning impulse current is flowing through the down air terminal, it will be having minimum of two parallel paths from the air terminal to the ground. So the current flowing through any down conductor will be always lesser than the current flowing through the air terminal. So that is the reason the air terminal will be always bigger in size than the down conductors. So this, as per the standard recommendation, we have to go for 176 square mm for air terminals and minimum 50 square mm for this down conductors. So when we are using any specific material on any specific configuration of the material for any specific condition, then we need to ensure that we are matching the minimum cross-sectional requirement for as per this particular standard. So this is for earthing material. So here also you can observe that we can use different materials, but they have removed aluminum because aluminum, even though it's a very good conductor, it should not be used below the soil because it corrodes much faster. So here also they have provided for different configuration. We can use rod or pipe or earthing conductor in the form of strips by plate. So when we are using in a rod configuration of any specific material, we need to ensure that we are matching the diameter provided by this particular standard recommendation. Right. So if we take this lightning protection system, we are nothing we are doing nothing other than providing a dedicated path for this lightning impulse current to discharge. So the continuity plays an important role. So we need to ensure that from the tip of the air terminal to the earth electrode, all the connections are proper. There are no loose connections in between. So the continuity is the most important parameter when it comes to this air termination system and down conductor system. So if the continuity is proper, then the system will definitely work fine. So we need to ensure all the connections are proper, and all the clamps are in good conditions. And one more thing is we need to ensure whether the earthing is in good condition or not, because we are receiving this energy and we are diverting it to the ground only. So if the earthing is proper, then most of the damages can be avoided. So the earthing plays an important role in ensuring the safety of the people and in discharging this current to the ground without much increase in the ground potential raise. So these are the points which we have to ensure while performing the maintenance of lightning protection system. These are some of our site observations. Here you can observe that the first image there is no air terminal at all. The second image there is they have placed this down conductor on the plate directly. There is no proper connection between air terminal and the down conductor. The third image, they have placed this lightning arrestor, then they have installed this handrail. But this air terminal should be the topmost point. But here the handrail is the topmost point. Even if any lightning approaches, it will strike on this handrail only. It won't strike on this air terminal. So the purpose itself is not solved. Here you can observe that in both the cases, the cable got disconnected. There is no proper connection to this earthing. Here, if you take this lightning protection system, the most important thing is the equipotential bonding. So if you are having many metallic structures near this down conductor, it should be connected to maintain the uniform potential. If the uniform potential is not maintained, then there will be a flashover between this lightning conductor and the other metallic part. So it may result in huge explosion or accident also. Here, the equipotential bonding is not done properly. And in the second image, the connection was made using a steel rope. That is not at all advisable. Okay, the standard has mentioned that the minimum cross-section area has to be 50 square mm. But here they have used only 6 square mm and 10 square mm cable. It is not at all acceptable. So the second important component is the earthing. So if you take this earthing, the earthing is nothing but the process of providing a dedicated low resistance path for the fault current or any abnormal current to discharge. So here we are providing a dedicated path so that the lightning current or other current won't be flowing to the body itself. So uh, the main thing is we have to provide a dedicated and low resistance path for this current to discharge. And in all the cases, there won't be any current flowing through this particular thing. Only during any abnormal conditions or during lightning conditions alone, the current will be flowing through this earthing. So depending upon the connections, the earthing can be classified into two types. If I'm connecting the body of an equipment to the earthing, it is called as equipment earthing or body earthing. So I'm connecting the neutral of the system to the grounding. It is called as system earthing. Right. So as I mentioned, during this discharge of current into the ground potential itself will increase. At normal conditions, we'll be referring this ground potential as zero voltage, but at the time of fault current discharge, the ground potential won't be at zero voltage, and it will increase to a greater value. And this voltage will drop suddenly if you move away from this earth electrode. Here you can observe that the potential is much higher, very near to this earth electrode, and if you move away from the earth electrode, the potential is keep on reducing. So here the potential is much higher, and somewhere away from this earth electrode, the potential is much lower. So there will be a huge potential difference between the points. So that is the reason to maintain the potential near the earth electrode very lower, we will be using this highly conductive earth enhancing compound. So whenever the ground potential increase is happening, then the two important parameters that has to be considered is the step and touch voltages. So if any metallic structure is becoming live, then if I'm making a contact by touching the structure, then because of the potential difference between the two objects, the current will be flowing through our body. So if you take this particular case, the body of this particular structure is at very high potential and our foot is at low potential. So because of this difference in potential, the current will be flowing through our body and the person might get electrocuted. Since this damage is caused by touching the structure, it is called as touch potential. And the second one is step potential. In this case, there is no need for direct contact also. If the ground potential is increasing and if there is a sufficient potential difference between the two foot, and because of the potential difference, the current will be circulating through the body and the person might get electrocuted. So the step voltage is very much dangerous because there is no need for direct contact also. Fine. So then what is the purpose of earthing? So as I mentioned, the primary purpose of earthing is to ensure the safety of the people. And apart from that, if we are having 230 volt or 240 volt, then we should have a reference point. The earthing will be acting as a reference point. And if you are going for the substations, the earthing should be designed for keeping the step and touch voltages within the limit. And one more thing is, if you take the substations, you'll be having lot of equipments for protection. For the proper operation of these protective equipments, for the protective equipments also, this earthing is very much essential. So if you take this earthing, there are three main components are there. One is earth electrode, second one is earth enhancing compound, and third one is terminal connectors. So the terminal connectors are also very much important. Even though if the conductors are good, and even if I'm using very highly conductive material, then if the terminal connection is not proper, there is no purpose in it. The current won't get discharged properly. So the terminal connection is also as important as the earth electrode which we are using. So whenever we are discussing about this earthing, the first question that comes to everyone is the earth resistance value. So before entering into that earth resistance value, first we need to understand what is this earth resistance value which we are discussing here. So if you take the resistance, we are using the resistance in our day-to-day life, but the resistance which we are discussing is nothing but ohmic resistance. That is, if I have a conductor, then if a current is flowing through this particular conductor, this conductor will be providing some opposition. So the resistance offered by this particular material for the current to reach from one end to other end. So that is from the point A to B. If the current is flowing, this material is offering some resistance. This is called as ohmic resistance. Here this ohmic resistance does not depend upon the surrounding material and all. So it is particularly depends upon the particular material alone. It does not depend upon any other surrounding medium. Here the conduction is taking place on the particular medium alone. It does not depend upon any other medium. Whereas in earthing, the dissipation is taking place from the earth electrode to the surrounding environment. So if this is the earth electrode, the conduction is taking place from the earth electrode to the soil. So it mainly depends upon the surrounding medium. If the soil has very high resistance, then the earth resistance value will be also higher. So here that performance mainly depends upon the surrounding environment, and the standard highlights that the resistance associated with earthing is electrolytic in nature. So the resistance which we are discussing in earthing is not the same resistance which we are discussing for the cables. So whenever we are buying a cable from the market, if you take the data sheet, they will mention the resistance per meter length of the conductor, but that is ohmic resistance. But in earthing, we are discussing about this electrolytic resistance. Both are different. Both are not the same. So before entering into the earth resistance part, we need to understand that the earthing which we use in day-to-day life are different from the earth resistance value. The earth resistance is electrolytic in nature, and it mainly depends upon the soil surrounding the environment, and it does not mainly depend upon the material which we are using. So, as I mentioned, the soil resistance mainly depends upon the soil resistivity, and the soil resistivity mainly depends upon the moisture and the salt content. If the soil has more moisture, then the soil resistivity will be lesser. If the soil has more salt content also, the soil resistivity will be lesser. So the soil resistivity again depends upon two parameters. So that is the reason you won't measure the soil resistivity during rainy conditions, because the moisture content in the soil will be higher. If the moisture content is more, then the value which we are measuring will be always lower than the actual value. So that is the reason all the measurements should be taken carried out at the dry conditions, not on the rainy conditions. So this is soil resistivity values provided by the standard IS 3043 for different types of soil. So if you observe in this table itself, they have provided The soil resistivity value based upon the moisture content. The first value is for normal and high rainfall, whereas the second one is for lower rainfall. So from this table also you can observe the impact of moisture level on the soil resistivity values. The second one is corrosion. So since we are using this earth electrode directly on the soil, the corrosion displays an important role. Fine. So, as I mentioned earlier, aluminum is not at all used for earthing. The main reason is, even though it is a very good conductor, but it corrodes much faster when used in the soil. So, when we are working with earthing, apart from this conductivity, the corrosion resistance property also plays an important role. So, the corrosion is associated with the type of soil which we are using. If the soil resistivity is much lesser, which means that the particular soil contains more amount of minerals and salt. So if the minerals and salts are more, then the corrosion rate also will be more. So lower the soil resistivity, greater will be the corrosion rate. So that is the reason here they mentioned the soil resistivity is less than 25 ohm meter, it will be severely corrosive. On the other hand, if the soil resistivity is more than 100 ohm meter, then the minerals and salts on the particular soil is much lesser. Since the minerals and salts are much lesser, the corrosion rate will be much lesser. So if I'm having a soil site condition which is having very low resistivity as 10 ohm meter for example, in this case I can easily achieve lower earth resistance value, but the problem is the lifetime of the earth electrodes will be much lesser because the soil is severely corrosive in nature. So the lifetime of the earth electrodes which you are using depends upon the type of soil which you are using on that particular locality. Right. So the first component is earth electrodes. The earth electrodes, the purpose of the earth electrode is to dissipate the fault current into the soil. So if this has to dissipate the fault current, then it should be able to withstand the fault current. If it is able to withstand, then only it can dissipate. And apart from this particular property, the second most important thing is the corrosion resistance property of the material. So aluminum, even though a very good conductor, is not preferable for earthing because of this poor corrosion resistance property. So that is also one of the most important parameters required for the earth electrodes. The standard has highlighted four different types of earth electrodes, that is plate, rod, pipe, and the strips. So if you take the plate earth electrode, generally we'll be using 600 by 600, and depending upon the material, the thickness will be different. The reason for different thickness is to compensate the effect of corrosion. The corrosion rate is much lower for copper. That is the reason we use only 3 mm thick plates. Whereas if I'm going for a GA or steel, then the thickness has to be 6.3. Whereas if it is from cast iron, the thickness has to be 12 mm. So the thickness is more not for reducing resistance value, whereas it is for compensating the effect of corrosion. So to provide the same lifetime. So this is a formula provided by the standard for calculating the resistance value of different configurations. So first one is plate earthing, second one is pipe or rod, and third one is strips. So if you observe closely, in all the formulas, we are considering the rho, that is the resistivity of the soil. So the resistivity of the soil plays an important role, and all other parameters are related to the dimensions of the electrode. Here we are not at all considering the material of the electrode. Either it can be copper or GA or cast iron or aluminum, it can be anything. But we are not at all considering the material because in earthing, the material does not come into the picture because it is electrolytic resistance. The impact of resistance of the material will be much lesser, whereas the impact of the soil resistivity is much higher. So that is the reason in all the formula we'll be considering the resistivity of the soil and we won't be considering the resistivity of the material. So this is just a comparison for the earth resistance value for different soil resistivity. So in the first case, we are having 10 ohm meter. Then for the same earth electrode, this is a pipe of dia 76 mm and 3 meter long, the resistance value will be 2.3 meters. So if I'm going for a 100 ohm meter, then the value will be around 23. If I'm going for 1000 ohm meter soil, it will be 231. So from this, you can observe that we cannot provide a standard resistance value for the type of electrode. So some people will be telling if you use this particular rod, then you can achieve less than 5 ohms in all the soil conditions. Then it is not at all possible. In earthing, the resistance value depends upon the soil resistivity only. If I am installing a rod which many people are telling that if you install, you will achieve less than 5 ohms on a soil resistivity of 1000 ohm meter, then the value will be definitely greater than 200 ohms. So don't believe those kind of words on the earthing mainly depends upon the soil resistivity. For that only we have provided this particular slide. So here you can see in all the three cases, the diameter of the pipe, material of the pipe, length of the pipe, all are same. But we are getting three different values and there is a huge difference between these values also. The main reason is the soil resistivity. So if the soil resistivity changes, earth resistance also will change. It is not at all possible to achieve the particular lower resistance value in all the type of soils. So if I'm getting a higher resistance value, then how can we reduce this value? So the standard has provided a different options like by increasing the diameter or increasing the length, then by increasing the number of electrodes or by providing this enhancing compound. So we can use any of this particular process for reducing the earth resistance values. So if you take this parallel connection, which is commonly used by many people, so many people are using this particular formula which we use for calculating the resistance value of multiple resistors. So if we are having two resistors in parallel, the combined resistors will be R by 2. If we are having three resistors in parallel, the combined resistance will be R by 3. So this is the formula many people are commonly using for earthing also. But this is not at all applicable to earthing because the formula which we are seeing here is for ohmic resistance. It does not depend upon the surrounding environment, but the resistance which we are using in earthing is electrolytic environment, which mainly depends upon the surrounding environment. So the formula which is used for electronic circuits is not at all applicable to earthing. The standard has provided the formula for calculating combined resistance also. So when we are working with earthing, then we have to use any of the formula provided by the standard. And one more thing is when we are going for parallel connection, the spacing between the electrodes plays an important role. We need to ensure the spacing of minimum of equal to the length of the electrode. If I'm using 3-meter electrode, then the spacing should be minimum of 3 meter. So that should be ensured. If I'm having very lower spacing, then the resistance value will be more. So that is the reason we mentioned it depends upon the surrounding environment. If I'm having two electrodes, if I'm installing at 1 meter spacing, 3 meter spacing, and 6 meter spacing, obviously the resistance value will be different for different configurations because it depends upon the spacing between the earth electrodes also. And most important thing is the current carrying capacity. How based for this current carrying capacity only, we'll be deciding the size of the conductor. So the standard has provided the formula for calculating this cross section current carrying capacity also. Here you can observe that I by S is equal to K into 1 by root T. So if I go for I, it will be SK by root T. So from this, we can calculate the what would be the cross section area of the particular conductor. So whenever we are working with cross-section area, the most important thing is whether we are working for a safer area or hazardous area. So if you take normal area, which is a safer area, the final temperature will be considered as 500 degrees centigrade. Whereas if you are going for hazardous area, the final temperature will be restricted to 200 degrees centigrade. Because of this restriction in the final temperature, the current carrying capacity of the conductor will be lesser because whenever current flows through any conductor, heat will be produced. The heat produced will be proportional to I squared into R. So if I am resting the final temperature, then the current carrying capacity of the particular material also will be lesser. So when I am working for an hazardous area, that is oil storage area and all, then I should not use this formula. Here I am using this final temperature 500 degrees centigrade. This is not at all applicable for oil storage area because it is hazardous. So for example, if I'm having a fault current of 30 kA, then in that case, using a 48 mm dia of class C, which is having 36 kiloamps, is more than sufficient for safer area. But if I'm going for a hazardous area, the same pipe is rated only for 25 kiloamps. So I should not use 48 mm dia. So I have to increase the size or either I have to go for class C pipe. So when we are working with hazardous that is oil phase area, we should keep in mind about this final temperature on the particular area. So the current carrying capacity of a material will be different for safer area and hazardous area. When we are working with hazardous area, then we should use this final temperature as 200 degrees centigrade only. We should not use the previous one. So the second component is earth enhancing compound. So many people will be considering that we are replacing the soil with the compounds only for achieving lower resistance. So that is not the actual case. So if I'm working with very low soil resistivity conditions where the corrosion rate will be more. So in order to protect the earth electrode from the corrosion, this compound will be coming into the picture. So this compound avoids this direct interaction between the soil and the earth electrode so that it protects the earth electrode from the corrosion. Since we are directly dumping it on the soil, the standard has explained about 4 different testings that are required for this particular compound. So we need to ensure that the compound is completely tested before using it. So these are the different standards which explains about interconnecting the earthing of lighting production system with other equipment. So the first one is from OISD GDN 180. Here they may highlight that lighting mass earthing can be connected with tank earthing. And the second one is from 62305. Here also they mentioned that lightning production earthing can be linked with the power system earthing. This one is from IS 732. Here also they interconnect the lightning production system earthing with other earthing. So this one is the reference from latest NEC 2023. Here also you can observe that the body earthing of the equipment is connected to the main earthing which is below the ground level. That is all the earthings are connected below the ground level. So the lightning production earthing can be interlinked with the earthing of other systems. So as I mentioned, the earthing resistance associated with the earthing is electrolytic in nature. It can be measured by injecting the current through the soil only. So we will be injecting the current between the current source and the test electrode, and we will be measuring the voltage drop between the potential electrode and the test electrode. The ratio of voltage to current will be the resistance. So that is how we will be measuring the resistance value. The standard has provided about different methodologies. Among the different methodologies, we are using Hall of potential 61.8 method. Here you can observe that the ratio of these two spikes will be maintained at 61 percentage. If I'm having the second spike at 100 meter, then the first spike will be at 61 meter. So if I'm having the second spike at 10 meter, the first spike will be at 6.2 meter. So we have to maintain the ratio. So we can use either analog meters or digital meters for measuring the purpose. So this is earth resistance. Here you can observe that the strips looks fine above the soil, but it was completely corroded when we remove the first layer of the soil. So here you can see that the pipe is very good from outside, but when we remove the top layer of the soil, there is no connection to the remaining part. So from both the images, you can observe that the rate of corrosion is much higher at the point the pipe is entering into the soil. So at the particular portion will be rate of corrosion will be more. And if you want to check the actual condition of the conductor, we have to remove the top layer of the soil and we have to check the condition at this point. So these are different observations. So in the first image, the connection is not proper. Second one, it is corroded. Third one, they didn't, that is concrete waste. In this, there is a air gap between the clamp and the conductor. The air gap, the connection is not proper. That is what we mentioned. The terminal connection should be proper to avoid this air gaps and loose connections and all. Thank you. So today we have covered about this outline of earthing and what are the different methodologies provided by the standard for designing this air termination system for oil and natural gas industries. So apart from this, we have conducted a separate webinar for lighting protection system, earthing, and risk assessment for different fields. So if you want more details regarding that, you can refer to the video. We have shared this link for the YouTube channel in the chat box also. You can refer to that. Any queries?